Okay, so what we are going to do today is we are going to talk about the first half of section 6.2, and then the second half of 6.2 we are going to do next time on Wednesday for B2. So you should have your yellow notes packet out. So our objectives are that we want to find x and y intercepts of rational functions, find vertical and horizontal asymptotes, find holes, analyze graphs, rationalize or graph rational functions by hand. So to start off, I'm going to kind of switch between the calculator and this for part of the time, but for the first half today, you will have really not need a calculator. So just a review of vertical asymptotes, which hopefully makes sense to you because all the vertical asymptotes are excluded values. So whenever the denominator, whatever would make our denominator 0 is our excluded value. So our excluded value in these, in part A, would be x is equal to negative 2. That would be the vertical asymptote. In part B, it would be x is equal to 5. In part C, it would be, if we factored this denominator, it would be x plus 2, x minus 2. So our vertical asymptotes would be x equals 2 and negative 2. So another way of graphing, instead of doing like what we did last time and changing our form to be in like graphing form, we can just plot points. So we can figure out what the x and y intercepts are by plugging in 0 for x and 0 for y. So if I plug in 0 for x, plug in 0 there, there, and there, that would make all of those 0, leaving me with negative 12 or negative 6, which is positive 2. So my y-intercept is the point 0, 2. If I want to find an x-intercept, then I should plug in 0 for y. And the only way that this whole graph is going to be 0, or this whole equation, is if the numerator is 0. So really, you just need to set your numerator equal to 0. You could also think about it as cross multiplying. So I'd have 3x minus 12 equals 0 times anything would be 0, so equals 0. And then solve for x. So I would end up with 3x equals 12, so x is equal to 4. With that, we want to write the point as an ordered pair, so my actual x-intercept would be 4, 0. I'm going to go through these pretty quickly because I think that's pretty simple. So if I plug in 0 for x, then my y value is negative 3/2. So that would be my y-intercept. And my x-intercept would be when this part is equal to 0. So if I factor that, I'd get x minus 3 and x plus 1. So my zeros are negative or positive 3 and negative 1. So I actually have two x-intercepts. They would be 3, 0 and negative 1, 0. So it's possible to have two. So the y-intercept over here, if I plug in 0, would be negative 5, 6. So my y-intercept would be 0, negative 5, 6. And my x-intercepts would be when my numerator is equal to 0, which would end up being positive 5/3 if I set 3x minus 5 equal to 0 and solve. So it would be 5/3, 0. So these are going to come in handy so that when we are trying to graph by hand. So next we're going to talk about asymptotes. So it says check for holes before you find your vertical asymptotes. So vertical asymptotes, we just wrote down where our excluded values. Well, they're a little bit more specific than that. They are our excluded values after we simplify our function. So for example, in this case, we can cross out x minus 2 and x minus 2, which just leaves us with x minus 3. So the x minus 2 that we canceled out from our original equation, x cannot be equal to 2. That is not technically a vertical asymptote, that is just a hole. So we have a hole on anything that we can cancel out, any value of x, and we have a vertical asymptote with anything that would be left in the denominator. So We'll move on. So identify any holes and then find all vertical asymptotes. So I need to factor always. So this will give me x plus 3x minus 3 in my numerator over x minus 3x plus, or x minus 2. So x minus 3 would cancel, meaning that I have a hole at x equals 3, and I'm left with x plus 3 over x minus 2, meaning that I have a vertical asymptote at x is equal to 2. So when I'm graphing this, I know that I'm going to have a vertical asymptote at x equals 2, but I am going to have a hole in my graph at x equals 3. Okay, so horizontal asymptotes. We're not really going to look for patterns. I'm kind of just going to tell you as we go. So in this case, we have a vertical or a horizontal asymptote at y equals 1, which comes from the coefficients of your leading coefficients being divided by each other, because x and x have the same degree. So if your degrees are the same for your leading coefficient in the, or well, for your leading term in the numerator and denominator, then you're going to have a horizontal asymptote at whatever the coefficients are divided by one another. So 1 divided by 1 is 1. On this next one, if it were multiplied out, we would have an x squared from here over an x, which means it's called the top-heavy graph, which we're going to talk about actually next time. But it actually has this end behavior model that looks something like this. So it's a diagonal that is going on, and it's coming from its leading terms and what they simplify to be. So x squared over x, would it simplify to be x? So the line y equals x is an asymptote, which we'll get to. We'll talk to you about later. And then the last one down here is we have like our highest power is x on top of degree 1 over x squared on the bottom. So this is called a bottom heavy graph. Anytime you have a bottom heavy graph or bottom heavy equation, that means you have a horizontal asymptote at y equals 0. And it summarizes on the next page for you. So we have an asymptote at y equals 0. And then in this last one, we can kind of see we have the same degree in the numerator and denominator. So our horizontal asymptote is going to come from this coefficient divided by this coefficient. So 2 divided by 1 is 2. So our horizontal asymptote is at y equals 2. Okay, so end behavior, which is horizontal asymptotes and others. So to find them, compare the degrees of the numerator and the denominator. If it's top heavy, we'll talk about that next time. If it's bottom heavy, then it has a horizontal asymptote at y equals 0, and if they are equal, then it has a horizontal asymptote at whatever the leading coefficients divided are. So we are going to identify the x and y intercepts, vertical and horizontal asymptotes, end behavior, and then make a sketch. So on this one, we could do it from how we did it last time, because we do have the graphs, or it's in graphing form, but we'll do it by x and y intercepts. So the y-intercept in this case, if I plug in 0, is negative 3 over 1 is positive 3. So my y-intercept is 0, 3. And my x-intercept, if I plug in x for y and set the numerator equal to that, I would get 0 equals negative 3, which is not true, which means I don't have an x-intercept. My vertical asymptote would be at x equals 1. And a horizontal asymptote, this is a bottom-heavy graph, so it has a horizontal asymptote at y equals 0. And then I can graph from there. So the negative 3 is going to, as we can kind of see with the y-intercept, going to make it a little reflected over the x-axis, so it'll be down here as well. And the end behavior would be as follows. So we would have the limit as of f of x as x approaches negative infinity is approaching 0, the limit of f of x as limit of f of x as x approaches positive infinity is also equal to 0. And there's our sketch. Yeah, so that's what we need for that one. This next one, so we're going to do the same type of thing. So our y-intercept, it would be 0 and 7/2. Our x-intercept would be plugging in 0 and setting the numerator equal to that, so 3x minus 7 would end up being 7/3, 0. I have a vertical asymptote at x equals 2, and I have a horizontal asymptote at 3 divided by 1 because these are the same degree, so that would be at y equals 3. So at y equals 3 and x equals 2, I have my asymptotes, and then I can draw my y and x intercepts. So 0, 7 would be 3.5, so 0, 3.5, somewhere up here. And 7/3, 0 is a little bit bigger, past 2, right there. So we can kind of already tell our graph is going to look like this. As you're graphing these, feel free to plug into your calculator to double check. Okay, and then we'll start this next time.